I've just realised I have an hour for this talk. I normally do it in 40 to 50 minutes, but it's sort of at a breakneck speed. So I can speak more slowly and make point number one. Yep. Oh, slightly closer. Ooh, that's weird. I still feel like I should be dancing with this headset on. Is that better? Yes. Okay. Okay, that sounds very weird with the speaker behind my head. I'm like talking to myself from the back of my head. We're hiring, but that probably doesn't mean very much in Austria, so because it's Tiger Leads in California. Okay, are we good to go?
Which part of California?
The dry part. Yeah, LA, West LA. Recurse. Okay. NYTProf. Has anybody not heard of NYTProf? What's NYTProf? Look at that, fabulous. Did you? Okay. For those people who've not heard of NYTProf, are you familiar with Devel DProf? Yes. So Devel DProf used to be the most common way of profiling your Perl code, but it's completely broken. And here we generate 100 subroutines, all doing the same thing, and we profile it with Devel DProf. And Devel DProf says we spent all our time in 4 of them. And what's happening there is Devel DProf uses a slow clock, and the clock happened to go tick when it was in those 4 subroutines. And that's completely insane, and the faster machines get, the worse Devel DProf is broken. So you just delete it, never run Devel DProf. So, profiling. What do we measure, and how do we measure it? Who prefers to measure CPU time? Yep, CPU time, yeah, you kind of care how fast the thing works, so you measure CPU time because you don't want to be disturbed by anything else running on system, so you measure CPU time. Grand. Who prefers profiling subroutines or profiling lines? Subroutines? Some people, lines. Yeah, a bit of a mix. Okay, so subroutine profiling, you're measuring the difference between the time you entered the subroutine and the time you left. And we call that I call that the inclusive time. And if you do that for every subroutine that one calls, then as you recurse back out, you can calculate the exclusive time, the time you just spent in that subroutine, by subtracting the times below. And what NYTProf does is it does that in real time as it's recursing out. So it actually keeps track of both the inclusive and exclusive at the same time. Subroutine profiling is really fast because the subroutine profiler is only involved when you enter and leave a subroutine. But the traditional problem with subroutine profilers is that they could get very confused by funky control flows. So things like autoload, things like goto, things like next out of a subroutine. And it was also very hard, if you've got a very large subroutine, it's hard to see where the time is spent within the subroutine. So the profiler may say, oh, that's really slow, and you look at it and it's 500 lines, and you go, what am I going to do with that? But when you measure when you do statement profiling, what you're doing is you're measuring the time from when you start executing a line of code to when you start executing some other line of code. Now, typically that would be the very next line of code, but it might be a line of code somewhere completely different if you're calling a subroutine, for example. So if you have a line of code that calls several subroutines, things get quite confusing because you start on the particular line and then you go off to another line and then you come back to this one. So the timings kind of get a bit weird. It's hard to think about that. But you do get the fine-grained detail. You get to see the time spent on every line, assuming your statement profiler is accurate. But statement profilers weren't very popular in Perl because they're really slow, and they're slow because the profiler is involved for every single statement. Yeah. So for subroutine profilers, the profiler is only involved when you enter and when you leave a subroutine. But for statement profilers, they're very involved. So traditionally, all the Perl statement profilers would be very slow. Slight problem also with statement profilers, if you imagine the logic is you measure the time from starting one statement to the time of starting the next. If you have a loop, well, how do you measure where do you put the timing for the loop condition? Where is that measured, and how is it measured, and how is it allocated? NYTProf goes to some length to try to apportion that as best it can into the right place. But if you only have a statement profiler, when you profile your code, you just get lots of timings for all the statements, and it's hard to think about how your logic is structured, because you don't get subroutine timings. You get lots of little fine-grained timings for individual lines, but you'd have to add them up in your head to work out how much time is spent in a subroutine. So, actually, to go back here, what NYTProf does is it just says, well, there's no right solution, so we'll have both of them. So NYTProf is both the statement profiler and a subroutine profiler at the same time. By default, they're both enabled, but you can turn one off or the other one off. Not much point in turning off both, but can be useful. So the next question then is, well, do we measure CPU time or real time? So CPU time, it's the time you're actually on the CPU, and the CPU is working on your behalf, running your program. And that has the advantage that it's not much affected by what else is running on the machine. And it doesn't include the time you spent waiting for I/O. Okay, it doesn't include the time spent waiting for I/O, doesn't include the time spent waiting for disk or network or anything else you might be waiting for. It's just the time the CPU is working on your behalf. The alternative is to measure real time, the elapsed time from start to end of the program. And that is affected by what else your system might be doing. If your system's busy doing something else, then obviously your code's going to run slower. And it includes the time spent waiting. Yeah. So, who would prefer to use CPU time? A few hands. Prefer to use real time? Okay. If your system is slow, is it slow in CPU time or is it slow in real time? Well, if you're bothering to profile it, it's because you think it's slow. And if you think it's slow in real time. Yeah. The reason that it's slow is unlikely to be purely CPU efficiency. It's probably slow for a whole bunch of reasons to do with waiting. Waiting for CPU, waiting for disk I/O, waiting for network I/O, waiting for locks, waiting for memory, waiting for caches, the whole works. If you only measure CPU time, you're missing a lot of insight into where your elapsed time is going. Yeah, so the only time when it's worth measuring CPU time, I think, is if you're actually looking at optimizations in the Perl interpreter itself, when it makes sense to say, am I using the CPU more efficiently? So if your focus of your profiling is actually CPU time, then fair enough, measure CPU time. But if you want your code to run faster in real time, then measure real time. Okay, NYTProf. The name is an accident of history. I do not work for the New York Times. I have never worked for the New York Times. I have no affiliation whatsoever with the New York Times. The New York Times last contributed many years ago. Okay, the number of times I get asked at conferences, so what's it like working for the New York Times? I don't work for the New York Times. Okay, to run NYTProf, Perl-D, or you can also run it this way, not much difference, a few subtle, obscure cases. You can configure how NYTProf behaves by setting the NYTProf environment variable. If you're trying to profile something where you can't control the Perl command line, then you can use this Perl5 opt environment variable. Slight downside with that is it'll affect any Perl interpreters that get run. So if you're trying to profile something that you don't control and it might fork off several Perl processes, well, if you do this, they'll all get profiled, but you can work around that by setting this add PID equals 1. And you'll get a whole bunch of NYTProf profiles generated, but they'll all have a process ID attached to the file name. And what you get out is that NYTProf.out file. Then you need to turn that into a human-readable report. That's just a big chunk of binary. Kcache grind, I've not used this myself. It was contributed a few years ago, but it does make these very nice diagrams which graphically represent where the inclusive time and exclusive time is spent in your subroutines. Has anyone used Kcache grind? Yay, there you go. So try this out and tell me if it's as awesome as it looks. Okay, so what most people do is they generate a HTML report with the NYTProf HTML command. You could read that, but I'll just demonstrate it shortly. It looks like this, or at least that's one page. The sort of the main index page looks like this. It starts off with a nice little summary. Often, if you've not profiled the code before, there's usually one or two obvious problems. And first page of the report, you go, why is all my time being spent there? And then you fix that and job done. Explain all this. So when the program was profiled, when you generated the report, summary, all of these are links into the source code. You can go off and look at all the subroutines. Most of the tables in the report are sortable if you click on the headings. It also tells you about subroutines. Sorry, you notice two things here. It's giving you, it's profiling built-in Perl subroutines. These are actually opcodes. And these are, I think this is an old picture. I think they're now labeled as opcodes rather than xsubs, but it'll flag the xsubs too. Okay. I get asked quite a lot of questions about inclusive time versus exclusive time, so I wrote this little diagram here. Time is flowing along, you call the foo subroutine, you enter the foo subroutine, bless you, Gesundheit, and you return. So that's inclusive time. But if that subroutine calls some others, then the same kind of thing happens. And there we go. These are the inclusive times of subbar, the time you actually spent executing the code in subbar. And then that, as you come out, gives you the exclusive time when you were in foo and not anywhere else. So the exclusive time is the time you were exclusively executing code in subfoo. Does that make sense? Excellent. So if you look back here, you see you've got two columns, the inclusive time and the exclusive time. So I'll explain in another few slides, I think, about when to focus on each, because there's sort of two different ways of looking at your problem. Okay, here we go. So inclusive time is best for a sort of top-down view. If you imagine you have some a program that spends some time loading some data, spends some time manipulating data, and spends some time writing it out, then a top-down view, you'd be able to say, well, how much of the time is it spent am I spending loading the data? How much of my time am I spending manipulating it and spitting it out? Exclusive time is best from a bottom-up perspective. Exclusive time says, in which subroutines was I spending my time? But that perspective is, unless you're familiar with the structure of the code, it doesn't give you a big picture. It's got to write down in the details. So, yeah. So the way to think of it is inclusive time is top-down, gives you a high-level view. Exclusive time is bottom-up. Okay. In the report pages, which I'll show you shortly, you can see all your source code is annotated, or it's presented in this table structure with the line numbers, and also has the annotations added. And they're added as if they're source code comments, just from a sort of stylistic convention. And you get a little extra detail here. This statement is the number of individual statements executed on that line. So for usual simple statements, it would just be one. This is a timing from the statement profiler. So that's how much time was spent between executing this line, starting to execute this line, and starting to execute the next one. Calls is the number of calls that the subroutine profiler says were made. So here you can see there's a call to wrap wanted and a call to find opt. So there were two subroutine calls made, and this is the amount of time spent in subroutines. So you can see here the two calls, so many milliseconds in this one, so many microseconds in that one. So this indented information here is about the where the control flow went from this, this line. So every line that has calls will have this annotation. And up above at the beginning of each subroutine, there'll be a block that shows you information for every place that calls into your subroutine. So essentially, there's like a tree of information coming into the subroutine and then a tree coming out from every subroutine call. Hey, look, that's all these notes. I haven't looked at these slides for a while, which is why I keep surprising myself, which, as somebody said earlier, is not good. So, all these slides are available online. This is another way of looking at the information. It's a tree map, and I apologize, and I continue to apologize for the coloring. The coloring is appalling, but it's kind of hard to fix for obscure reasons. What the colors tell you is really just a grouping, a visual grouping of blocks. This is a view, this is a tree map of the exclusive time. So this is a bottom-up view of the time spent in all the subroutines within your application. And I don't remember what this is. Oh yes, this is Perl Critic. Haha. Haha, this is Perl Critic. This is my go-to example for NYTProf. So the size of the box is the relative time spent in that subroutine. So big boxes are things to focus on if you think that the proportion of time spent in there is too much. And as you hover over the boxes, you get that little panel showing you extra information. I will demo shortly, and then it might make more sense. Another kind of visualization that NYTProf produces is this graph viz. And I thought when I did this originally that it would be kind of really cool and lovely. And it is for these trivial examples. It looks kind of nice, and you go, oh yeah, that's sweet. And here it's sort of starting to get a little bit more busy, but you can see there's only a handful of subroutines. I used to demo real examples of significant applications, but it would just keep crashing graphics, and it would take hours to generate, and it was just a complete failure. So I don't think anybody uses this now, but it's there if you want to experiment with it. It actually generates the dot files. So if you have something that can do something useful with dot files, then they're generated for you. Any questions? Multiple threads. Thank you very much for asking the question. I can't answer. It doesn't handle multiple threads. Well, let me rephrase that. It ignores profiling for any thread other than the thread it was enabled in. So it doesn't crash, I think. Basically, it's if you run NYTProf in a Perl that's been built for threads, then it keeps track of the thread that it was enabled on. And if ever the internals get called on a different thread, it just says, I'm going to ignore you. So the effect is that you get a profile of just the thread that you started NYTProf on.
So if it has some child threads, then we are not going to have any information about it.
No, you'll only get information for the main thread. Okay, so, and a slightly more subtle complication occurs with co-row, because co-row is kind of threads that aren't threads. Only the author would say that it's the only threads, but that's another story. So it's also broken for co-row. Now, it probably wouldn't take a huge amount of work to fix. So if somebody wants to fix it, then talk to me. But you'd have to be familiar with how to make C code thread safe. It's just I've not done it. I've not been motivated to do it, but it wouldn't take a lot of work. Okay, demo time. So here is Perl Critic. And I like to run Perl Critic on its own source code, just because I'm kind of that way. So here's Perl Critic running on a chunk of source code. And then here's Perl Critic running under NYTProf. And you see it's slightly slower. It's about twice as slow when you run something under NYTProf. I think it's a little bit less than that. Again, if you turn off statement profiling, it'll be a lot faster. So generally, if you're trying to profile something that's performance sensitive and the slowdown, the overhead of NYTProf is too much, try turning off the statement profiler, and you know, the cost of NYTProf will go down. Then to generate a report, you just run NYTProf command. Actually, I should show you. So it's generated this NYTProf.out file there. And you can generate NYTProf.html will generate your HTML report, and the open flag just says, well, generate the report and then open it. So I will pause for a moment. And then say, ta-da, hopefully timed well. There you go, ta-da. Now you can see that the slide I had previously was a bit out of date because now we have this awesome flame graph. So, there you are. What else do you need to know? That just explains it all. You're welcome. I mean, thank Brendan Gregg for inventing this flame graph visualization. It's a wonderful way of capturing where the time has been spent. So I'll explain a little about what the flame graph visualization is. Effectively, height is stack depth. So right at the bottom here, we have and width is time. So this is the whole program, and all of it was 4.7 million microseconds, so that's 100% of the time. And you can see almost all of it was spent in run, and 96.92%. And then there's this little thing over here, which was a begin, and that begin called another begin. So this was kind of all the initial setting up. This would be loading the modules. You can see the time in there, token quote. So you can just roll up here and you can see one thing calling another. This is stack depth. But we don't care about that much because that's not wide. This is the thick bit. So we spent our time in run, and run called critique, and critiques underscore critique. And that spent a chunk of time here with the begin, and there's a whole bunch more begins here. Loading modules, module pluggable policies. So this will be loading all the policies and getting initialized. Then over here we have critique. So this is where it's actually starting to do real work. And there's the document. And in it from external source. So here you can see it's doing the lexing. So it's lexing. And then over here we gather the violations. And what are we doing? Bit of processing. And then over here I think that's initialization. What you'll often see is, well, what you can see here is chunks. This is a big chunk of time, and the width is giving you the proportion of the time spent in that part of the code. Have I explained that sufficiently well? It's kind of, I don't think I'm doing a good job explaining it, but hopefully it's just sufficiently clear that width is what you care about. So things that are narrow but tall, don't worry about that. It's whether the width as a proportion is representative of what you think the time should be spent. I'm not explaining this very well, so my apologies for that. I'll carry on. Sorry? What are the colours? Oh, thank you. What are the colours? The colours are completely meaningless. It's called a flame graph simply because the colours are flame kind of colours. Brendan Gregg, who invented visualization, has kind of tried to explore assigning meanings to the colours, but there wasn't a sufficiently useful way of doing it. There's been an attempt to be able to diff flame graphs and assign colder colours to things that have got smaller, but I don't think that's got very far. Essentially, the colours are completely random. I do have a patch request. So I have a bug report suggesting that the organisation, because the organisation left to right for any given stack depth is purely alphabetical, which is another thing that I should have explained and now have. So thank you. But it could be organised slightly differently, and then you'd be able to visually diff. You'd just be able to switch between two flame graphs to kind of get a clearer visual sense of whether you have made a change. I'm not explaining that very well. So I shall move on. Ooh.
Can you click one of the...
Yes, thank you very much. So as you hover here, Actually, and then that reminds me of another point. So as you hover here, you can see you get a pointer, and I can click on one of those, and it takes me straight to that subroutine.
Expecting for another flame graph.
Oh. Aha! You'd like another flame graph to appear focused on that
Exactly.
subroutine. that would be lovely, but it's not going to happen. Effectively, the flame graph for, well, so here's an interesting point. An individual subroutine can appear on a flame graph in multiple places. Okay, because so you'll often find that up in the leaves of the flame. What would you call the tips of flames? I guess you'd call it tips of flames. Up in the tips, you'll find utility functions and utility methods that may be called from a lot of different places. So if you were to click on a node, you could, in theory, create another flame graph where you aggregated together all of the stack frames that subroutine was involved in, where it called out to other things. So it would be doable. One of the kind of the architectural problems or mistakes, you might say, with NYTProf is that it just generates static HTML reports. And that was fine at the start, but as the reports have got richer and richer, it would be nice to, instead of pre-generating everything, to have a back end that could be queried, and then the reports could be dynamic. And then it would be easier to do this sort of, let's generate more interesting information at this point, because it could be generated dynamically. But that would require a lot of work to sort of re-engineer the way the reports are generated and the way the data is processed. So, well, I should explain another point about the flame graph. Is the flame graph is built by an external utility that Brendan Gregg wrote, and it just takes a very simple text file and spits out an SVG. So something that I've done occasionally is to grep the text file, because the line format is just all the stack frames that each subroutine was involved in. So you can grep the data file for the subroutine you're interested in, and then pass the output of grep into the flame graph, and that will give you, I think, what you're interested in. So, send me a patch. But it's one of those things where it wouldn't make sense to generate a flame graph for every subroutine in the entire program. So it's one of those places where it might make a nice little separate tool, but architecturally it wouldn't fit in with the way the NYTProf works at the moment. Okay. So there's that summary table that I showed you with the inclusive times and exclusive times. These are ordered by the exclusive time. So what you're seeing is the individual subroutines where most of the time was spent. And you see that Perl Critic spends most of its time doing match regular expression. So that core match is the name of the opcode where the time was spent. And underneath that was, or the next one be PPI node find, which is used by the rules, the Perl Critic rules, to explore the DOM that it's built as it's parsed the Perl code. Down here you can see all the source code files, ordered by time spent in the source code file. So you can see most of the time is spent in inflecting. Now that's an interesting thing. I hadn't thought about that before. Why is most of the time spent inflecting? That seems like something that might be fixable. Let's go and take a look. So here we are in lingua en inflect core match. Why are we there? Let's look at that. Whoa, this gets called a lot. So here we can see all the things that have called it. Now, because it's an opcode, we don't have any source code. There's no Perl source code. So we've created this dummy subroutine as just a way of reporting on where the time was spent. So it's flagged as an opcode. But these are all the different places that have called it. So let's see what's called it the most. We've called 3,000 times here by inflect post process. So we click on that, And that takes us up here, post-process, fixed pedantry and capitalization. Why are we calling this so much? I don't know. We were called by, in fact, PL, and that was called by pod word list. Pod word list. Ooh, copy word list. I don't know. Yeah, so this sounds like it's something, because we're now not in a subroutine, we're in a module, pod word list. So it seems like this is some bootstrapping code. So there's time spent bootstrapping that could be looked at. So I don't want to give a whole presentation on optimizing Perl Critic, but I hope you can see that you can explore through your code. I've used Perl Critic sometimes if I've got a new code base that I'm trying to understand. I'll use it for something with profiling enabled, and then I'll just be able to follow the links. Click up, click down, and just see how the control flow has moved around the code. Any questions about this?
Is it possible to measure the memory consumption?
Ah, memory profiling. That's a whole separate talk I have on memory profiling. The answer is no. NYTProf itself doesn't do any memory profiling. And it's a much harder problem than you might imagine. I've given talks on it, so just go look up the talks and then weep quietly to yourself. Okay, so what I want to talk about now in the last half hour or so is optimizing. So there's a great tool here, and the tool gives you a lot of information, and the information is pretty accurate. But then the question is, well, what do you do with the information? You know, it's saying, hey, this bit of code's slow, too much time being spent here. What are you going to do about that? Okay. Whenever we talk about performance, there are so many subtle details involved that you should never take anybody else's word for anything. So always do your own testing on your own Perl binary, on your own hardware and your own circumstances. Don't believe anything I say. So, for example, beware twos. Twos are like really bad. Just don't use twos in your program whatsoever. They just cause endless problems. Just remove them.
It's okay, my 2 key is dead.
So does anyone know what's going on here?
End of block.
End of block, yeah. So remember, this is a statement profiler, and it's measuring the time between starting one statement and starting the next statement. Where is the next statement after the two? Well, that's a good question. I think so. NYTProf intercepts the opcode that is used to exit the loop in order to correctly end the timing of that statement, but it's still not as accurate as it could be. So if you do lots of calls, then the error adds up. There's actually an option you can use to disable that in NYTProf, so you can see the effect. But it's enabled by default because generally it helps. Now here's another example. 2 calls to exactly the same code, and the second one's faster. Anyone know why? Caching. Caching, yeah. So assuming that subref is fairly small, simple, when the second call is made, all the code is already in the CPU caches. You know, probably not the level 1 cache because Perl is so vast that nothing fits in the level 1 cache when using Perl. But the level 2 cache, and maybe level 3 cache if you have one, so everything's going to be lined up ready. So for the second call, it's going to work faster. And note here, this some expensive sub. So what that some expensive sub is doing is something really heavy that's wiping the caches of anything related to that subref. So when you call the subref twice, what you get in the cache for the second call is what you needed in the cache, was what's left over in the cache from the first call. So there can be subtle effects. If these were 2 similar things, but not identical, you'd look at that, oh, I must rush off and optimize this one, but I won't worry about this one. Do you see? So these timings can lead you astray. You need to think about what's going on under the hood. But again, you only notice these effects when you're doing very tight loops. But it's something to keep in mind. Okay. So I've given you some warnings. We are about to enter risky territory. So you're all professional programmers, or most of you are professional programmers. And as professional programmers, you've learned to do certain things and not do certain things. You're entering now a world where you will throw out all those good lessons that you've learned in the name of achieving performance. So the first rule of programming optimization by Michael Jackson, not the Michael Jackson you might be familiar with, is don't do it. Just don't do it. And the second rule for experts only mind, is don't do it yet. Why? Yeah, why not, actually? Why not? Why not go and optimize all your code straight away? Why not spend many happy afternoons optimizing your code? Well, the reason is that you're going to do bad things. You know, you will not be able to look at yourself in the mirror after doing what you will do in the name of performance. Including blind stupidity. So, a lot of people know this quote. We should forget about the small efficiencies. Premature optimization is the root of all evil. But you know, we shouldn't pass up the critical 3%. If you are facing a problem where you need more performance, you know, where you actually need more performance, not you'd like more performance, but you'd need more performance, then yes, then it's time to start work. But how? What do you do? First thing, throw hardware at it. Don't touch the software, because you know, touching software is dangerous business. Hardware is cheap. Professionals, programmers are very expensive and also very error prone. So much better just throw hardware at it. Faster boxes, more boxes. Definitely don't touch the software. Hardware upgrades are usually much cheaper and less risky. Okay, you can't do that. You know, you've got the fastest hardware that your boss will allow you to buy. So the next thing is, don't try to guess. Now that's where you need a good tool like NYTProf. Don't try to guess where these things are, because they're often not where you think they are. Yeah? And this is an old carpenter's maxim. Be really sure you understand what's happening before you start making changes. So the way I approach optimizing code is, first, don't do it. Please can I have faster hardware? But then if you want to make changes, then do the simple stuff first. And often things will just jump out at you. So I'll get the code, I'll ask it to do some reasonable bit of work with the profiler running. I'll look at the exclusive times of the subroutines. Remember, that's the bottom-up view. And just, do they look reasonable? Yeah? Often something will jump out at you. There'll be some subroutine. Hey, why am I spending so much time there? Look at the worst offenders, both the code of the worst offenders and maybe why they're being called so much if they're called a lot. Only fix the simple, obvious problems. You know, something should jump out at you. Profile it again. If it's fast enough, stop. You know, put the profiler down, walk away. And often just doing that, something will jump out at you. You go, oh yeah, hadn't thought of that. You'll fix it with a simple change. Job done. Move on to something else. What do I mean by simple local fixes? I just mean any change that you can be sure is, or at least reasonably sure, is not going to introduce bugs. So a very common one is to move invariant expressions out of loops. Do I have an example? No. Often I'll see loops where there's some initialization, and the initialization is the same every time, and it could just be moved out of the loop. Very simple thing. Another one I see very often is repeated chains of accessors. So you've got some object and you call down a chain of accessors, and then maybe the very next line, call down the same chain of accessors. Just put like the first few into a temporary variable and then use the temporary variable rather than repeating them. Use faster accessors. I think at the time I wrote this slide there was a lot of evolution and competition in this space. I think now things have settled down, but often you could get useful performance improvements just by using a faster accessor generator module. Another thing I find a lot is calling subroutines that aren't actually necessary to call. And the kind of the classic case here would be logging. Often logging, when you call a logging function, especially at the debug level, it's not going to go anywhere because logging's normally turned off. But the code might spend quite a lot of time preparing the arguments to pass to the debug function, which is then going to say, oh, debugging's turned off. So what you can do, most logging libraries will allow you to say, is a certain logging level turned on, and get a Boolean, and then only bother preparing the arguments and calling the method if it's going to do something useful. Okay, another very simple one. Often there's a lot of initialization at the beginning of a subroutine. And then the subroutine says, well, I don't need to do anything in this particular case, so just returns. So just return early. Get out of the subroutine early before you've done any expensive initializations. Just return as fast as you can. So delay expensive initializations. This is an actual patch from some code in some in a very hot path of a production system. So this is identical to this. But whoever wrote that wasn't terribly familiar with Perl. So there's just silly code that could just be written in a more idiomatic way. Sometimes you'll run across a regular expression that looks innocent, but actually can be a huge time suck. And because of this, or this reason is why NYTProf profiles opcodes in order to get insight into slow regular expressions. Normally they're very fast, but just occasionally you'll run across one that's pathological, and it might not jump out at you if you didn't get the timings. Another very common performance optimization in hot code is just not unpacking the variables. So you'll often see code that unpacks the variables and then just delegates to something else in it. You can avoid that. And similarly here, this shift avoids unpacking the variables. Very simple optimizations, very easy to reason about and to just type out without risking bugs. Another one I come across a few times in hot code, if you've got capturing parens in regexes that you don't need, easy to remove. So you've done those kind of things on the subroutines that have stood out. And generally that's enough. Most of the time, that's going to give you enough of a performance boost. So, what do? Yes, you retest fast enough, stop, put the profiler down, walk away, go and have some lunch. But if you need more performance after making those kind of changes, then it's getting a little more serious. So what I do then is I would reprofile with a known workload. So the typical case here would be a web service. And I'd give the web service a number of requests, of identical requests. So maybe 1,000. So I'd say 1,000 requests. There's something reasonable, some bit of work that would be representative of the production work, but 1,000 identical requests. And what that lets you do is to check the call counts. And what you'll often find is that you've asked it to do 1,000 of the same thing, and you'll find there's some subroutine that gets called 10,000 times. And you go, oh, hang on a sec, why is that being called 10,000 times? Or you'll find something that's being called 1,000 times when it should have been called just once, because it should have just been an initialization. It should have just been called once, but for some reason it's being called every time. And those things can just really stand out very easily. You've given it a known workload of 1,000 requests, and you can just look at the numbers and go, well, that makes sense, that doesn't make sense, and then go and investigate. Nick?
We found the flame graph was excellent for that.
Yes, thank you. Yeah, flame graph really shows, well, hang on, no, flame graph would show depth, or do you mean width in terms of? Yep.
Yeah, the flame graph was awesome. We just found that the flame graph was really wide. Why are there lots of things happening above this point?
Right.
And it was something that should have been cached that was not being cached,
yeah.
and being called many, many times when it should have been once. Right. Exactly this.
Great. So call counts can tell you a lot, but in order for them to be meaningful, you have to know exactly what work you asked the program to do. So hence the known workload, like 1,000 of the same thing. Excuse me. Okay. And the next one is to check the inclusive times. Now this works well with batch jobs, where you're doing the sort of the traditional load a bunch of data, process a bunch of data, spit it out. And then you can just look at the inclusive times from a top-down perspective and say, well, is the distribution of time right? You know, you might expect to spend 10% of the time loading, 80% processing, 10% writing. But if you actually find you spend 50% of the time loading, then clearly something's not right. So here the percentages of the time spent looking at the inclusive times will give you a sense of, you know, is it reasonable? What you're asking yourself here is, are these reasonable call counts? Is this a reasonable percentage of time? And what happens in the call count case especially is that caching is the antidote. And whenever caching is the antidote, you can easily give yourself another problem. Okay? There's a reason that computer scientists say that, what is it, the three, all three, the three hardest problems in computer science are naming and caching validation and off by one errors. There we are.
Caching is an off by one error.
Caching is an off by one error.
Yes. It's off by one level of indirection.
Yes, yes. So, there are, you can solve any problem in computer science by adding a level of redirection, of indirection, except the problem of too many levels of indirection. That's a Larry Wall quote.
The second half.
The second half, yes. It's a Larry Wall addendum, or corollary. Okay, so we've seen how the NYTProf report makes it very easy to chase up and down the call tree, because it's giving you links. The annotations inside the subroutine show you the calls made down, and at the top of the subroutine shows you callers coming in. So what that allows you to do is very easily move up and down the call tree and find good places for caching. Yeah? So you'll be able to see that this thing was called 1,000 times from this place when you expected it to just be called once. And that's telling you that the caching up there is broken or that you need to add caching. Okay, another a good tip is creating objects that don't get used. And the classic example here is datetime. Datetime objects are fairly expensive to create and they're quite heavy. So if, for example, if you're doing log processing, you might be reading lots of logs and generating datetime objects for all the log lines and then throwing most of them away. Yeah, it's very expensive. So a quick fix there that I've used is using some kind of lightweight proxy that's kind of very cheap to create, but it'll inflate itself into a datetime object if the need arises. And the same kind of concept can be used in lots of other cases. If you're creating objects but you're not really making much use of them, you could put in a lightweight proxy instead. Another tip that's kind of like throwing hardware at it is to throw a better compiler at it, or use a Perl that's been built with a more appropriate configuration. So these are good because you're not changing the software, and changing the software is risky. These are changing your Perl. So the threading support varies between platforms, and I've seen reports of 2% to 30%, and it varies between Perl versions too. But if you don't need thread support for any of your apps, then build yourself a Perl without it. I think Perl Brew defaults to not building a threaded Perl now. Avoid the Perl with debugging enabled. There's a debug flag for the Perl internals you can configure when you build a Perl. If you do that, that's quite expensive. Changing your malloc. I don't have recent information. Nick would be a good person to talk to about changing malloc. But for particular workloads, you may find that using the system malloc or using Perl's malloc or using a third-party malloc might change your performance profile. Use 64-bit, or maybe sometimes don't use 64-bit. Again, depending on the nature of the work you're trying to do. Or long doubles, not long doubles. Another interesting one is some commercial compilers that you pay big bucks for are actually worth the money, you know, if you're doing serious computing. Upgrade your Perl. Newer versions of Perl, surprisingly enough, generally go faster. I mean, thank Nick and many others for doing amazing work down in the Perl internals, making things faster, and lots of little micro optimizations that. Sorry?
Perl critic.
Perl critic. Yeah. Yeah. Is it? Yes. So there've been, I mean, Perl, NYTProf itself has sort of fed back into the Perl community, and a lot of the tools have got faster, and when the tools couldn't be made faster, sometimes the Perl has been made faster in order to make the tools faster. And that also, more recent Perl builds are much better with performance. Again, Nick and others have done sterling work on that. So, done all these kind of things, retest, fast enough, great. Put the profiler down, walk away. Because we're now going to get, you know, if you still need more performance, we're now into the really serious stuff. This is where you will create bugs just because of the nature of what you're trying to do. Well, having said that, this one's pretty easy. This should probably be in the previous section. I see this kind of thing a lot, where you've got a loop, or you've got something that you're iterating over. If this walk method does some, for example, checking permissions. Do you have permission to walk the dog? That's going to get repeated for every single dog. And maybe you could actually just add a method here and say, walk these dogs, and push the loop down. And if you push the loop down, you then get the opportunity to just do the precondition checks once, instead of paying the cost on every iteration of the loop. Faster modules. Sort key is a lovely module. If you're doing sorting and you find that sorting is a particular performance problem for you, sort key allows you to pre-generate optimized sort modules, sort functions. Use better serialization. Serial is a much better for serializing data than storable, much more performant. LWP, the grandfather of HTTP modules, HTTP Tiny, HTTP Lite, curl, hijack. These all lose functionality but gain performance. Yeah, so if you're only doing something simple, maybe this is enough, and this is really fast. But there's usually a trade-off. You know, you're losing features in order to gain performance most of the time, so you need to look. Neil Bowers has done a great series of reviews of various kinds of Perl modules, and it's often a good place to go. If he's done a review of the kind of modules you're looking at, like the HTTP, then he offers a lot of guidance, and he's done the research about kind of what features you lose and what you gain. Sometimes you're using hashes when you should be using arrays. Sometimes you're using arrays when you should be using hashes. Now, clearly, if you're in that sort of scenario and you're thinking about changing, then that's going to be a great source of bugs. But if you can pick a better data structure for the algorithm you're using, then that can be a big win. What algorithm are you using? Is it the right algorithm for what you're trying to do? You know, do you understand how the performance of the algorithm will change depending on the workload? Another thing I've found very helpful occasionally, there's been places where I've optimized the Perl code as far as I can. And I've ended up with some little bits of Perl code that are just as fast as they can possibly be. And then if I've needed more speed, then I've changed them to C. And I've used inline C at least once in production code, and it's worked very well. It allows you to effectively write C in the Perl file. You know, there can be occasional deployment issues because effectively you're requiring a compiler.
This is exactly what the grant of Ingi is going to fix.
All right. Okay. Ingi apparently has a grant to make this even better. But clearly you need to be able to write in C code, but it's a great fallback position. Small changes add up. Now, there was a. Let me rephrase that. I wrote this slide some time ago. You probably don't know Bill Raymond. He just optimized some software. But I read a blog post just the other day from the author of SQLite. Who uses SQLite? Yeah? The latest version of SQLite is 50% faster. 50%. And in the blog post, he says that there wasn't one big change. He didn't make one big change to achieve this. He made that 50% came from hundreds of tiny changes, each one of which was barely measurable. But they add up. Yeah? They add up fast. So here's, SQLite, very mature code. Used a lot of money has gone into optimizing that. And even now, they can still find a 50% speed up improvement by doing a lot of little optimizations. So that gives us all hope. There might not be any low-hanging fruit, but you can still make a big difference. What I've been talking about is very generic Perl changes. Perrin Harkins has a talk that's a much more high level, talking about particular modules and DBI and so forth. That's worth a look. Okay, any questions?
When I optimize a subroutine that I think that is just too slow, and rerun my benchmark and look at my profile, are there any tools that help me to look at, or to easily see that my profile is in that spots faster and in other spots slower?
So can you effectively do a diff of a
A
performance
diff of the heat
report?
map or something else?
No, there isn't at the moment, and that's an interesting problem, but it's one I've not devoted any time to. The topic came up recently in relation to flame graphs and whether it would be possible to just visually flip between flame graphs, and if the flame graph is structured a certain way, it should be possible just to visually see the impact of the change. So I think that's an interesting thing to explore. Certainly, if you have two profile data files, it ought to be possible to present the information about what's changed between them. But I haven't given it any work.
Would it be possible to
Oh, hang on a sec.
Would it be possible to filter out initialization phases? Because sometimes for convenience I use my test files for profiling, and there you have test more and all this stuff, which makes most of the time, more than 90%, because if I test pure Perl algorithms, then it's in the flame graph very, very slim.
Yes. Okay, so can you filter out the initialization phase?
Or something else?
Yes, and the answer is yes, you can. NYTProf actually has lots of options, and one of the options, okay, is init. Start, rather.
Okay.
Start. So, there we go. The default is to start profiling immediately, but you can also change the start to be init, and that says only start profiling once you've finished initializing the Perl code. So all your begin blocks and all your module loading stuff, all that just won't get profiled, and you can focus on the runtime. So that would be a good solution. Nick?
It was a sort of unquestioned. Can you confirm I think it ties into some of the things you were saying. The one I wanted to say about Perl Critic, if I remember correctly, was you profiled Perl Critic and you discovered it was spending a lot of time in ISA. And then that was because it was kicking all the way back down into the core, and the core ISA algorithm was in C, but a linear scan. And we replaced it with a hash lookup, which gets back to what you said about big O notation.
Yes.
That we used a better algorithm and sped up ISA lookup as a result of NYTProf. But again, it kicks back to the end of what Tim said about better algorithms. Better algorithms get you there faster.
Yeah.
And that was cool.
Thank you.
Ah, another question, Maris.
I have a question regarding Moose. I do work a lot with Moose, and I find it from time to time quite difficult to find out what's actually going on with all the anonymous subs and rounds and stuff like this. Are there any tools to help me with that, to show me the real name of the method?
Okay, Moose. So how can you get more insight into what Moose is doing? Several approaches. One slightly flippant one is to upgrade to Perl 6. Not quite so flippant as to maybe switch to Moo. NYTProf uses the name of the subroutine, and the names of the subroutines you get from Moose can be a bit weird. And it's hard to relate back. The short answer is that I don't have a good answer for you. The slightly longer answer is that it can be improved. There's a sub-name module on CPAM, which Moose uses, at least in some cases, to assign names to anonymous subroutines. So you can, for example, in your Moose code, wherever you use an anonymous subroutine, you can give that anonymous subroutine a name yourself. And that would give you some insight into those places where you're the one providing the anonymous subroutine. For Moose itself, you could probably submit patches that would enable the use of giving better names, but I don't have any more suggestions. There's lots of Moose developers here, or at least a few, so you could maybe talk to them about it. I'm not a big user of Moose myself. Well, I use it, but I don't develop with it, let's put it that way. Any more questions? Nope. Okay. Yes? No? No? Okay. I think we're done. Thank you.